All right, well, thanks for joining us today. We're here to talk about Beyond Regulatory Flood Hazard, incorporating BLE into master plans. My name is John Belines. I'm the South Watershed Manager with the Mile High Flood District. And we also have Haley Heineman with Dewberry and Danny Elsner with Dewberry. So a quick agenda of what we're going to be talking about today. We're going to go over briefly what a traditional watershed master plan, at least how the flood district does it, how that process is set up and where it came from. We're going to talk about base level engineering and what it is and how it sort of supplements or improves upon some of the aspects of a traditional watershed master plan. And we're going to use the City of Englewood MDP that the flood district in the City of Englewood currently have going on with Dewberry as a case study for both of these. I'll give you a second to enjoy our memes. One does not simply break tradition. So where did the traditional, what we now think of as the traditional MDP or OSP, Mile High Flood District Watershed Master Plan, come from? Just 4 years after the National Flood Insurance Act was passed in 1968, the Flood District published its first master plans for Weir and for Sanderson Gulches in 1972. And since then, we've used more or less the same process or very similar process that's evolved over the years for MDPs and FADs. And for those of you who don't know, MDP is a major drainage way plan, and FAD is flood hazard area delineation. And these have been our primary tools to inform our floodplain mapping and management programs. So what does that process look like? Some of you are familiar with this if you work in the flood district, others might not be. But for a traditional MDP and FAD, we do what we call baseline hydrology, which is a use of CUHP, which is our calibrated hydrologic model for the Denver metropolitan area, and SWIM. And then we do a 1D HEC-RAS hydraulic analysis. We do floodplain mapping when we're doing a FAD. Sometimes we don't, but often we do. We do an alternatives analysis and a conceptual design. And again, this is all based around kind of a 1D hydraulic modeling process with the assumptions that are baked into our hydrology. We have a drainage way of interest that we've selected and a watershed that we want to look at. We build our partnerships around that stream, and then we run this process basically from start to finish. And we've been doing studies like this for several decades. There's some common assumptions that are made, just simplifying assumptions that are necessary as a result of both the 1D hydraulic modeling that we do in HEC-RAS, as well as the way that we do floodplain administration. You're either in or out of the 100-year floodplain. I think we all are kind of aware of the pitfalls of that, but flood risk is not as simple as just being on one side of a line or another, but that's essentially the assumption that we're making for a 100-year FAD delineation. We're assuming with connectivity, we're assuming that the water in the basin gets to the stream and that it gets there in a relatively uninterrupted manner. That's not always the case. You see our last bullet here, we ignore localized flooding and ponding. We don't always see where that localized flooding and ponding might be happening or where there might be transfers between basins or between sub-watersheds. And a lot of times, obviously, we use 2D models to inform 1D models to help identify some of these issues that are kind of left out of the traditional process. So these assumptions and others beg the question of what we're missing in the traditional way that we've been doing master plans for the past number of years. With respect to urban flooding, NAFSMA said that non-riverine or pluvial flooding has not been adequately identified through technical modeling, mapping, or other techniques used in riverine risk identification, so that individuals living in urban areas are not aware of their flood potential. And actually 25% of all flood damages, approximately 25% of all flood damages occur outside of the mapped flood zone. And NAFSMA even went so far as to say that the flood hazard posed by urban flooding is just as significant as addressing riverine and coastal flooding. Yet it's obviously something that we don't typically account for, at least not in the traditional process that we've used.
Over the next few slides, I'll give a high-level review of what base-level engineering is and some ways it can be used to enhance and inform floodplain management at all agency levels. So what is base-level engineering? Base-level engineering is a methodology created by FEMA that prepares flood data in order to expand local risk awareness. BLE assessments are produced using high-resolution ground data to create technically credible flood hazard information that may be used to expand and modernize FEMA's current flood hazard inventory. Commonly, it takes the form of 1D or 2D HEC-RAS models that are watershed or citywide. They use LiDAR, they can be automated, and they usually have a manual model review. BLE modeling is similar to legacy approximate modeling, like Zone A's, but BLE allows an engineer to perform large-scale modeling in a fraction of the effort. And the output typically includes, but isn't limited to, floodplain boundaries, flood depths, and water surface elevation grids. Base level engineering can be used to assess the current validity of existing flood hazard inventory, or like I said, it can be used to estimate Zone A areas where little or no information exists. But base level engineering does not replace the information shown on any current effective firm panel or the results of a more detailed conventional flood hazard analysis. So capital improvement projects, mitigation projects, they should all still be based on our conventional H&H methodology. How does FEMA use it? So a significant portion of FEMA's National Flood Hazard Inventory is currently considered non-model backed or is based on outdated techniques with no supporting data. Also, FEMA is required to validate flood insurance rate maps every 5 years by reviewing flood hazard information and determining if the built environment or expected flood flows have changed since a previous study was performed. So to support those requirements, engineers have now started using base level engineering to prepare broad and accurate flood risk information for FEMA and communities nationwide. Once a base level engineering assessment is completed, FEMA releases that flood risk information to the estimated base flood elevation viewer. The elevation viewer is an interactive web portal that transforms thousands of models and data results into a few data sets to provide users the ability to review estimated flood extents for a variety of scenarios. For example, users on the BLE viewer website can download engineering models, floodplain extents, estimated flood depths, and water surface elevations, or even run a site-specific report to review flood risk information for their area. At a minimum, communities can use BLE results to supplement effective firms as the best available information when the BLE shows an area is flood prone and it's not currently depicted on a firm, or it's the most conservative BFE or floodplain result that exists. But beyond regulatory floodplain applications, the data sets may be used to inform future land use decisions, support grant submissions, generate flood vulnerability assessments, prioritize flood risk projects, and to design and prioritize capital improvement projects. Producing and sharing this data is an opportunity to broaden and expand risk awareness conversations with our local communities, ultimately strengthening disaster resilience and reducing public spending on recovery efforts after a flood event. The beauty of BLE is that it can be used in almost limitless ways, and FEMA has encouraged municipalities to think of unique ways that their community can put this data to work. These newer model-backed flood hazard areas are even making an impact in the number of communities and homeowners purchasing flood insurance because the models mimic what they're seeing in their day-to-day lives. So finally, the big question, how can it be used for master plans? The integration of BLE into our MDPs and FADs is a great way for us to modernize the Front Range master plan approach, ensuring we're doing our best to protect our community from flood risk. This slide lists just a few ways BLE can enhance master planning. For example, BLE is a time-efficient way for engineers and floodplain managers to practice their due diligence. Similar to collecting and reading previous studies, BLE can provide a quick picture of the watershed and some of its higher risk areas. This can lead to the identification of problems that were previously unknown or missed, and an expanded MD scope that can address those. BLE can also be used to inform our traditional methodologies like CUHP. Basin delineation can be guided or QC'd by radon-grid analysis, or BLE can be compared to existing storm sewer infrastructure to identify systems that buck grade or that may not be optimized. Results can be used to identify big changes to the floodplain as a result of large development, or could serve as a first cut model for the FAD phase. Reviewing results with the community or soliciting input from landowners can also help validate modeling, and it can gain community buy-in. And that's just the tip of the iceberg.
All right. So we're going to use, as I mentioned before, we're going to use the City of Englewood MDP as an example for kind of integrating base level engineering into the more traditional master plan process. So the City of Englewood MDP is a major drainageway plan that's underway right now between the flood district, the City of Englewood, and Dewberry. And there's a history of flood risk in the City of Englewood. For those of you who aren't familiar, it's just the very next southern suburb of Denver. The South Platte River runs right through the middle of it, and there's a history of flooding on the South Platte, obviously. And there's also a history of pretty severe urban flooding in the many direct tributary basins to the South Platte River from Englewood, particularly on the East Bank, but also on the West Bank as well. A young lady died in a basement in a home in the South Englewood Basin in 2018 during a major flood event. And that event kind of it precipitated this study as well as some other recent studies that have been done to try and get a handle on what the flood risk is in these urban areas and on these smaller streams that in many cases have really been completely obliterated, honestly, by development or built directly over. You can see the grid here in a portion of the City of Englewood where there used to be, or in the natural topography, is a major drainage way, but that no longer exists, and there's nothing but maybe some minor storm sewer and a trunk line storm sewer that doesn't carry the full 100-year event. So we know that there is flooding both from a fluvial aspect in these streams that no longer exist in the landscape, as well as pluvial flooding due to all of the imperviousness in the basin, the alleys and the obstructions that are very difficult to model in a traditional 1D scenario. Just because there's no channel in these areas doesn't mean there's no flooding, and just because there's no floodplain on the firm panel doesn't mean there's no flood risk. So the goal of this study is to really look comprehensively at all of the flood risks in all of the different major basins in the City of Englewood, do our traditional H&H analysis on these major drainage ways, as well as to identify potential local flood risk through the pluvial flood risk analysis that we're going to talk to you about here in a minute. And the ultimate goal of this study is to come up with an overall project prioritization for the entire city across drainage ways, including both pluvial and fluvial risks, to help mitigate what we know are severe and life-threatening flood risks to the citizens of Englewood.
So for the Englewood MDP's modeling, we customized the BLE methodology to the characteristics of flooding that we're seeing in Englewood and the city's goal of prioritization on mitigation projects. Our modeling adopted the latest high-resolution LiDAR for both our hydrology and our hydraulics. The hydrology was updated from old versions of CUHP to use the same NOAA Atlas 14 rainfall, the same land use projections, and a more consistent sub-basin size range. Our hydraulics modeling took things one step further than a conventional BLE by using 2D rain on grid rather than applying a hydrograph or peak flow at a specific location, which eliminated some engineering judgment and allowed the model to do the routing for us. In order to run rain on grid, we grabbed excess rainfall hydrographs from our updated CUHP models, and we ran a quick sensitivity analysis and determined that we could use a single averaged hydrograph across the entire city. This average excess rainfall hydrograph was applied to the rain on grid in 2D HECRADs, which was divided into pieces for faster run times. In this case, we were mainly focused on off floodplain flooding, so open channel bathymetry and hydraulic structure information wasn't incorporated. And this speaks to the flexibility of BLE and how you can optimize your efforts for the project you're working on. The results were reviewed for reasonability and compared to anecdotal information that was provided by Englewood residents for a recent OSP update by Caliber Engineering. The results gave us an approximation of areas of inundation that have been used to inform our traditional MDP and CUHP, our traditional MDP, CHP, and swim hydrology, and that will help with our alternatives analysis phase as well. So there were some important assumptions that we made for our BLE. First was the simplified hydrology so that we could use that rain on grid method. For other areas, it could be more appropriate to use more detailed inputs or your standard 2D modeling. But in this case, we found that it was the best way to capture the very complex flooding that occurs through the urbanized area of Englewood. We assumed a low frequency event like the 100-year storm would overcome the existing storm sewer infrastructure to a degree that we could ignore its effects. The industry is actively working on best practices to account for storm sewers in these situations, such as reducing the applied flows or reducing the final depths, but this is still a work in progress. And then Manning's N values were based on planimetric data and were then tweaked to account for obstructions like structures and reasonable parameter outputs like peak velocities. So this was our first foray into an MDP BLE combo, and it indicated advantages and some drawbacks. BLE is a time-efficient and cost-effective method of confirming a base-level understanding of a region's flood hazard. Engineers can gather the data and create a model that can be shared with the public or their client at a much faster rate than the previous legacy studies. The high-quality elevation data provides the foundation for more credible flood risk identification and can be further refined for more detailed analysis. Leveraging this high-quality topo and using improved technologies like a 2D hydraulic modeling software can significantly improve the accuracy and quality of flood studies, or at the very least, help us get there faster. Despite the many benefits of using BLE, there were some challenges that we faced. Accuracy is one of the big issues, and working at a large scale, it's easy to potentially miss hydraulic controls. We may find ourselves largely under or overestimating high water surface elevations or ignoring storm sewer capacities that need a closer look. It's important to reiterate that the information we gain from BLE is not cookie cutter or foolproof, but an innovative way to enhance our current processes.
So let's look at some of the results of the BLE, and just to be fancy, let's apply Google Earth just to show how that mixed together. You can see from our zoomed out point of view, we're showing the floodplain in blue, the pluvial flooding, again, from a rain on grid. I want to point out probably the lower part of the Broadway there, as you zoom in, that's where our development is developed right on top of the channel, and it's just crossing Broadway and not really following the roads, but following the low spots through houses and through the areas that we're talking about. Great example and confirmation of earlier studies and showing that flooding. Let's go identify some other low spots that we have here. Here's a location where our basin delineation did not cover or find this low spot, but our pluvial flooding did. As we zoom in, you'll notice that it's starting to show a low spot that has backed up water, that we're starting to see individual houses where the pluvial flooding is not spilling down the street, it's not being collected, and we need to identify this as an area of interest to do further study. This is not caught during normal basin delineations, but it sure feels like this is an area that we want to go farther, identify if this is a risk, and make sure that we're not seeing localized flooding or a depression area or lack of storm sewer. Another result to look at is how we take instead of the pluvial that we just looked at, how does the fluvial match up? Here's our rain on grid for dry gulch coming from the detailed study in blue, and our fluvial results, again, rain on grid, no swim, no CUHP, and what that looks in red, and how that identifies that floodplain, and what a very quick and simple look to see where that floodplain is, how that delineated, and where we should find areas of concern. It gives us approximate results, just like a zone A, like Haley talked about. We have an initial results to see what that floodplain looks like and where to zoom in and where to focus. It's not a defendable study. We still need to do that detailed study going forward, but it is a great first start to see where we should focus off and use that for a fluvial analysis. So what are our next steps? Of course, right now, working with the district, we are finalizing the basin hydrology. We also submitted a pluvial memorandum stating what we just showed and what that looks like. Really, our next step will be, like Haley was talking about, like John's been talking about, meeting with the city, showing them the results of the pluvial study, and seeing if we want to continue down a normal MDP path, or do we want to add information, whether it's further detailed studies like the low spot depression or other areas where further detailed analysis or maybe different information needs to be added. Again, the ultimate goal is to prioritize projects. So that could include additional pipes, additional inlets in those low spots, where to go, and what to do about that. The takeaways I want you to see for this project, or we want to see for this project, is that BLE is a useful tool. It's great for that first analysis and where to go. Where should we focus in on? What can we see from a pluvial or fluvial situation? And like Haley said, it can help us identify where basin delineations or basin transfers are occurring. Or like John said, where we can inform the public or the stakeholders what the actual risk is and then start to detail down where to go. It helps inform the community of these issues without a high level of engineering. It really is a quick and dirty way to get the answer and then see where you want to take the MDP from there.
So I want to give a quick plug for the new software that we're developing here at the Flood District called Confluence, which is a web-based application that displays mapping information about flood risk and problem prioritization, and is our new platform for taking in work requests from the local government, and will eventually be our platform for project management and for displaying the results of master planning studies such as these that we've talked about here today. The address is confluence.mhfd.org if you want to go take a look at it. But some of the things that we're thinking about doing with Confluence, or one thing that we're actively working on, is developing this data set of what we call problem areas. And you can see some of them here in these big red polygons that are shown on the map. But the idea is that we're essentially distilling the results of our master planning studies and other studies that we've done into distinct areas that represent flood risk problems and eventually stream health problems and other things that can allow users to identify and prioritize their issues in their jurisdiction or in their county, whatever it might be, and then submit those directly to the flood district for funding and for improvements. And one thing that we're thinking about doing in the future with this base level engineering is, what if we were to do a rain on grid analysis for the whole flood district? Just drop an inch of rain on the DEM for the whole metro area, see what it tells us in terms of what I like to think of as kind of an initial triage of potential problems or areas of concern, as Danny mentioned earlier, and see if our detailed studies line up with that, or if they don't, or if there's potential areas where we might need to make a new detailed analysis to be able to validate the results of what we're seeing. And that can be based on information from topo that's derived from photogrammetry and other sources that can be updated on an annual basis instead of LiDAR, which is updated much less frequently. It could be based on local sources of topography. So there's a lot of potential out there for using BLE to derive new sources of information for identifying flood risk in the flood district and elsewhere. So this is just one example, and a quick shameless plug for Confluence. And with that, we'll be happy to take any questions that you have.